So hello everyone. Today I'm going to be doing lecture notes for a section covering ordering relations for our class. I know we already covered this in class a little bit, but because it is kind of a new topic and diverges a little bit from what we were covering before, namely equivalence relations, I thought maybe I would go over this section again. In particular, because this is also my first sort of interweb lecture, I thought it would be good if I did this section again. And so this is the way I'm going to be presenting these online lectures, is I'm not going to be presenting them as sort of 1 hour segments, but rather I'll be doing one section at a time. So in this particular lecture, however long it lasts, it's just going to be regarding ordering relations. Okay. So these are a little bit different than the equivalence relations we were discussing before. So remember, in general, we talked about relations, and then we talked about equivalence relations in particular, and how they gave sets that were defined on particular structure, namely in the form of equivalence classes, which then naturally formed a partition of the set. And so equivalence relations provided this really nice structure to the sets for which they were defined. And today we're going to be talking about ordering relations, which can give a different type of a structure to the sets that you define them upon. And so before I define an ordering relation, I thought it would be best to sort of illustrate some things with an example. So the classical example for an ordering relation is the following. So example. So we want to consider the less than or equal to relation on the real numbers, right? So what can we say about the greater than or the less than or equal to relation on the real numbers? Well, first, the relation less than or equal to is reflexive. That is, for all real numbers x, x is less than or equal to x. Furthermore, the relation less than or equal to is transitive. That is, if x, y, z are real numbers with x less than or equal to y and y less than or equal to z, then it follows that x is less than or equal to z. Right? Okay. But note that the less than or equal to relation is not symmetric. That is, x is less than or equal to y does not imply that y is less than or equal to x. E.g., 4 is less than or equal to 5, but 5 is not less than or equal to 4, right? Okay. So this relation doesn't satisfy the conditions to become a equivalence relation, but it does have some other properties. That is, so let's see what properties it does have. So let me just go to the new page. So, but this less than or equal to relation has two other properties. One, for all xy, real numbers, either x is less than or equal to y, or y is less than or equal to x. Okay, one of these is definitely true. Secondly, if x is less than or equal to y and y is less than or equal to x, then it follows that x equals y. Okay. Property 1 is called comparability. And property 2 is called anti-symmetric. It's called anti-symmetry. Okay, and so there are several other examples for which you can think of which don't satisfy all these properties, but for example, could be anti-symmetric or could follow comparable. But okay, but it's always a good example to relate. It's always a good idea to relate these back to the less than or equal to operation. Okay. All right. Now let me just give a precise definition for anti-symmetry because it's an important property. So let R be a relation on a set A R is anti-symmetric on A if and only if for all xy in A, if x is related to y and y is related to x, then x equals y. Okay, so when you're trying to prove that something is anti-symmetric, if you're trying to prove that a relation is anti-symmetric, what you do is you're allowed to assume that two elements are related to each other. So you're allowed to assume two elements, x, y, are related to each other. X is related to y, and y is related to x. And then you have to prove that x is equal to y based on those two assumptions. Okay, and so we can see some examples on this. Let's sort of get to the crowning definition of this section. So definition, a relation R on a set A is a partial ordering, I should say. Partial ordering for A if R is reflexive, anti-symmetric, and transitive. A set with partial ordering is called a partially ordered set or a poset. Okay. So let's see an example of this. So example. So let R be a relation on the natural numbers let X be R related to Y for X, Y in the natural numbers, if and only if X plus Y is even and X is less than or equal to Y. Okay? So let's verify that R is a partial ordering on the natural numbers. Okay? So first, reflexive. So let X be a natural number. So when you're trying to prove reflexivity, remember, you're not allowed to make really any assumptions about the things you take out from the set. Rather, you just try to take an arbitrary element out of the set and prove under the sort of the criterion of the relation that the element is related to itself. So what is the criterion on this relation is that if I take an element out of the set, if I take two elements out of the set, then they're related if when I add them together I get an even number, and if X is less than or equal to Y, the first element you take out is less than or equal to Y, the second element. So reflexive, I have to prove that an element is related to itself, right? So I'm taking the same element out of the set twice. And so if I just take an element out of the same element out of the set twice, does it satisfy these criteria? So is it reflexive? So yes, because note, X plus X is 2X, which is even. And X is less than or equal to X. So it's reflexive. Second, let's try transitive. So, is it transitive? So let X, Y, and Z be natural numbers with X related to Y and Y related to Z. Now we need to show X is related to Z. Okay, so now we're trying to prove something is transitive. We're allowed to assume that X is related to Y and Y is related to Z. So we have that X plus Y equals 2K and Y plus Z equals 2J for K, J, some natural numbers. That is to say, the sum of X and Y and the sum of Y and Z are both even. And we have that X is less than or equal to Y and Y is less than or equal to Z. Note, this immediately implies that X is less than or equal to Z. To complete the proof, what do we have to show? We have to show that X plus Z is even. So let's do that. So how do we show that? So we need to show x plus z is even. Note x plus y plus y plus z equals 2 times j plus k, which implies x plus z equals 2 times j plus k minus y. So x plus z is even. Lastly, to prove that R is a partial ordering of the natural numbers, we need to show that it's anti-symmetric. So how do we show it's anti-symmetric? Well, remember, we're allowed to assume that two natural numbers are related to each other. So x is all related to y, and y is all related to x. That is, x plus y and y plus x are both even, and x is less than or equal to y, and y is less than or equal to x. So these are all the things that we're allowed to assume if we're trying to prove that the relation is anti-symmetric for this particular problem. But notice this last bit of information here is something we talked about at the very beginning of this lecture, because we know that this less than or equal to relation is anti-symmetric. This information immediately implies that x is equal to y. And so we proved that R is anti-symmetric on the natural numbers. Therefore, R is a partial ordering for the natural numbers. Right? Okay. And there's several other examples you can think of. And one thing that I would like to do now is to take the opportunity here to look at some pictorial representations of partial ordering after we discuss this sort of natural theorem that emerges. So we discussed partial ordering. Now let's consider this theorem, which is kind of a naturally emerges from the discussion we just had before. So if R is a partial ordering for a set A, and x is all related to x1, x1 is all related to x2, x2 is all related to x3, and so on and so forth. And then you get that xn minus 1 is all related to xn. And then finally you get that xn is all related to x, so you sort of completed the loop, where all these x's are in A. Okay. And n is a natural number. Okay. Then in fact, all these elements we've extracted from A are equal. And this is sort of easy to think about in terms of what we were just discussing for anti-symmetric relations. And you can actually prove this on, you can prove this by using induction on the number of elements you're extracting from a given set A. Right? Okay. Now that we've talked about partial orderings in the abstract, sort of, for sets, we're going to talk about a more concrete definition, a type of a structure that partial ordering imposes upon the sets that it's defined upon. Okay? So I thought let's go to a new page. So definition. So let R be a partial ordering on a set A, right? And let A and B be elements from that set, with A not equal to B. Okay. Then A is an immediate predecessor So it's an immediate predecessor of B if and only if A is all related to B and there does not exist a C in A that is different from A and different from B, such that A is all related to C and C is all related to B. Okay. So let's start with a very sort of basic example here. Consider the less than or equal to relation on the set 1, 2, 3, 5, 8, and 10. So notice 2 is the immediate predecessor for 3. But 2 is not the immediate predecessor for 8 because 2 is less than or equal to 5 and 5 is less than or equal to 8. And so because I was able to find an element between 2 and 8 such that 2 was related to that number and then 5 was related and then the middle number was related to 8, 2 is not the immediate predecessor for 8. Right? Okay. So a little bit more abstract now. So let A be the following set: 1, 2, 3, 4, 5. So simple set. So let A equal 1, 2, 3, 4, 5, and consider the power set of A. Partially ordered under set inclusion or subset, right? So consider the set 2, 3, 5, right? Which is definitely an element of that power set, right? So what would be an immediate predecessor of this element in the power set of A? So that is, you want to find, so need to find x in the power set of A such that x is a subset of 2, 3, 5, and you can't find any, and you can't find y in the power set of A with x a subset of y and y a subset of 2, 3, 5. Right? That's what it means to find an immediate predecessor. So what's an immediate predecessor of the set 2, 3, 5? And you might find that there are several immediate predecessors. So for example, the set 2, 3 is a subset of 2, 3, 5. And it's not a subset of really any other set that's between these two. Also, 2, 5 is a subset of 2, 3, 5. And you can't really find any other set that lies in between these two. And furthermore, 3, 5 is a subset of 2, 3, 5. And so all are immediate predecessors of the set 2, 3, 5. So it's pretty cool. And so there need not be a unique immediate predecessor for an element in a set under a partial ordering. So this example this example shows that. Okay. And so when we introduced relations, we talked about digraphs that could capture the information shown in a relation, given by a relation. And with partial orderings, digraphs can be given even some more structure. So consider the following example. So example. Let m equal 1, 2, 3, 5, 6, 10, 15, and 30. And with divides partial ordering. And you can think about this set in terms of partial orderings and how these all are related to each other. But for partially ordered sets, it's oftentimes easier to draw them in a particular way. In particular, first you want to find the element that has no immediate predecessors under this ordering in this set. And if you look carefully at the set, the element in the set that has no immediate predecessor is 1. And so you're going to take that element and draw it at the bottom here. Okay? And 1 is obviously related to itself, so we're going to draw an arrow. Now, what is 1 the immediate predecessor for? So under the divides relation, what elements is 1 the immediate predecessor for? And if you look carefully, it's actually 2, 3, and 5. So in the next row, in this diagraph, we're going to draw 2, 3, and 5. And 1 is the immediate predecessor for all these. And again, all these elements are related to themselves because partial orderings are reflexive. And now we think, what is 2 an immediate predecessor for? Well, 6, right? Because 2 divides 6, and you can't find anything between 2 and 6 such that 2 would divide that, right? And that number would divide 6, okay? But 2 is also an immediate predecessor for 10. And you might say, well, 5 is between 2 and 10, but remember, we're thinking about this in terms of divides relation. And even though 5 is between 2 and 10, and 5 divides 10, 2 does not divide 5, and so 2 does not violate the immediate predecessor property in that regard. And similarly, 15. 2 is not an immediate predecessor for 15. Rather, if you continue the process for 3 now, 3 is also an immediate predecessor for 6, but it's also an immediate predecessor for 15. And 5 is an immediate predecessor for 10 and 15. Okay, so you can then draw the arrows here. And there's these loop-de-loops, and there's only one element left. And so you just complete the graph. And so a nice way to draw partially ordered sets is to again start at the bottom and put element with no immediate predecessor, IP, okay? And then in the row above the element with no immediate predecessor, you draw all the elements that the element in the below row is an immediate predecessor for. So 1 is an immediate predecessor for 2, 3, and 5. And then in the row above the second row, you're going to write all the elements for which the elements in the second row are immediate predecessor for. So 6, 10, and 15. 2, 3, and 5 are immediate predecessors for 6, 10, and 15. And then at the very top, you put the element that is not immediate predecessor for any element. So if you look at this graph, and if you draw the digraph for the partially ordered set in this way, you'll notice that all the arrows point in the upward direction. Right? There's a directionality to this graph. And all the elements, all the nodes have sort of a loop. And so if you know you're drawing a digraph for a partially ordered set, and you draw it in this particular way, there's a reduced way in which you can draw it. And so this is called the Haase diagram. And because we assume that the directionality is towards the top, we can just draw the nodes in the exact way that we had them listed when we drew the full graph, but we're not going to include arrows, and we're just going to include the edges. and it's understood that the directionality of the graph is from bottom to top, and it's also understood that all the nodes have loops on them. And so this is the Haase diagram for divides, right? It's what we just drew. Right? Okay, so let's draw another Haase diagram. So example. Let A equal 1, 2, 3. Let's draw Haase diagram for the power set of A under the partial ordering subset. Okay, so in this case, it might be easier to sort of write out the elements. And notice that because A is such a small set, you can actually write out the power set because there's only 2 to the third 8 elements in it. So we have the empty set, we have the set containing 1, the set containing 2, the set containing 3. So remember, I'm just writing out all the subsets of the set A here. The set containing 1, 2, the set containing 2, 3, and the set containing 1, 3. And I have one set left. What is that set? And then we have the set A itself, right? Okay. And we want to draw the Haase diagram for this set under the subset. And so remember, what we first have to do is ask ourselves, what is the element in this set for which there is no immediate predecessor? And that should be easy enough. It's just the empty set. That should be at the bottom. And which elements is the empty set an immediate predecessor for? Well, it's going to be the singletons. So we draw them in the next row, and we connect them with lines. Now, what is the set containing 1, just the set 1, just the element 1, an immediate predecessor for? Well, it's going to be an immediate predecessor for 1, 2, and 1, 3. What about 2? 2 is going to be an immediate predecessor for 1, 2, and 2, 3. And 3 is going to be an immediate predecessor for 1, 3, and 2, 3. And so you can draw all these edges this way, and at the top up here, you have the set A itself. And so that's the Haase diagram. Sorry, it's a bit messy, but that is the Haase diagram. And so it works out nicely. Okay, now with these immediate predecessors and things like this, all well defined, all defined nicely now, we can delve into some more structure here. And so this is going to be a long definition, but let's just get right to it. So definition. So remember, and maybe I haven't made this as clear as I wanted to, but as we work our way through the section, but a partial ordering of a set gives a set sort of a definitive type of order. It's not about equivalency, but rather we have this sort of comparability that a partial ordering sort of gives to a given set. So I want you to make sure you keep that in mind. Whereas when we talked about equivalence relations, we were thinking about the equality of different structures that were sort of created by equivalence relations. Here, we're thinking about relations that are imposing comparability between the different elements of a set. Okay, and in that spirit, let R be a partial ordering for a set A. Let B be a subset of A, and let A be an element of A. Then A is an upper bound. Okay, A is an upper bound for B if and only if B is related to A for all B in B. So I've taken a subset out of A, and that subset has an upper bound if I can find some element in A that is bigger in some sense than all the elements in that subset. Similarly, A is a lower bound for B if and only if A is related to B for all B in B. Okay. A is a least upper bound. Kind of sounds oxymoronic if you say it the first time, but it does make sense. Or supremum for B if and only if A is an upper bound for B and A is all related to X for every upper bound X for B. Okay, so it's kind of like the tightest upper bound for a subset B. Okay, and so let's finish off this definition. So this is the definition continued. A is a greatest lower bound for B, or infimum, I don't know how to say that actually, infimum for B, if and only if 1, A is a lower bound for B, and X is related to A for every lower bound X for B. Okay, so A is the infimum for B if it's a lower bound for B, and any other lower bound you find for B is related to A. Okay, so you have these sort of symmetric definitions for greatest lower bound or least upper bound. In fact, soon we'll see that there's at most one supremum and one infimum for a set. So in fact, even though I've written A greatest lower bound and A least upper bound for B, they will in fact be unique. Okay, so we're going to go straight into an example here, and it's going to be sort of be a, well, maybe we'll start off with an easy example. Okay, so so consider just the interval 0, 1, right? So you're just considering the interval 0, 1 of R. So I'm just going to write some facts about this. 2 is an upper bound for 0, 1. Okay. So we're thinking about the real numbers in terms of, you know, the standard less than or equal to relation. -5 is a lower bound for 0, 1. The supremum here is 1. And so maybe one thing you can ask yourself is, what is the infimum? And I'll let you think about that. So next, now that we've sort of developed intuition here, let's go a little bit more abstract. So let A equal the following set, just basically 1 through 10. So 1, 2, 3, 9, 10. And let B be equal to the following. So the set containing the set 1, 4, 5, 7, 1, 4, 7, 8, and 2, 4, 7. And so this is a subset of the power set of A. And so we're thinking about the subset partial ordering. So now we ask ourselves, what is the infimum? What is the supremum? You know, what is a lower bound? What is the upper bound for this? And so on and so forth. Okay, so you think we can do this? So let's do it. So what you might notice is that this set one, 2, 3, 4, 5, 6, 7, 8 is an upper bound for B because 1, 4, 5, 7 is a subset of B. Is a subset of. Okay, I'm going to call this N. Is a subset of N. 1, 4, 7, 8 is a subset of n, and 2, 4, 7 is a subset of n. So n is an upper bound for B, because I found a set that contains each of these sets. Okay, but the lower bound, sorry, it's not the least upper bound, right? Because note, if I just removed no, so if I, okay, right, so 1, 2, 4, 5. So notice that the elements that contain these three, that sort of comprise these sets I've written on the left here, are basically 1, 2, 4, 7, 8. So the supremum of B is going to be the set 1, 2, 4, 7, 8. So n here is not the most efficient because it also has three, actually that might not even be right. 1, 2, 4, I missed one. 1, 2, 4, 5, 7, 8. Okay, so this setup here, n, has 3 in it and a 6 in it, and neither of those are needed to be an upper bound for the elements in B. What about an infimum? Can you find what is the infimum of this set? So what about infimum? Well, you know that the lower bound would obviously be the empty set, because it's a subset of every other set. But can we do better? I think we can. Notice there's a set here, 4, 7, which is a subset of 1, 4, 5, 7, is a subset of 1, 4, 7, 8, and it's a subset of 2, 4, 7. And the empty set is a subset of 4, 7. And you can try, for as long as you want, to see if you can find a set for which 4, 7 is a subset, and then it's still the set you find is a subset of these three listed I've listed above here, but I don't think you would find it. You could try though, again. Right, yeah, you can try, but I don't think you'll be able to do it. So indeed the infimum for the set B is this set 4, 7. Okay. Okay. Now to that theorem I promised to tell you about, and this is a pretty cool theorem and actually a pretty important theorem when you get into things like analysis and things like this. So let R be a partial ordering for a set A, right? And let B be a subset of A. If the supremum of B exists, it is unique. Also, if the infimum of B exists, it is unique. So, yeah. Okay, so let's prove this. So yeah, sorry if my notes are a little bit crazy. It's the first time I'm trying to do a lecture on the interwebs for you guys. I hope to get better at this as time goes on, but yeah. So the way to do this, the way that we typically do uniqueness proofs is to assume that, because we're trying to show that there's only exists one supremum, is to assume that two exist. So assume x, y are both supremums for B. Then both x, y are upper bounds for B by definition, right? And because x and y are both supremums and x and y are both upper bounds, it follows, by definition, that x is related to y and y is related to x, right? Because to obtain this first part here, what you do is you say, well, x is the supremum for B and y is an upper bound for B, therefore x must be related to y. And similarly, to obtain the second part here, you say, well, y is a supremum for B and x is an upper bound for B, and so y must be related to x. Since R is anti-symmetric, x equals y. And so there we have it. We proved that the supremum for a set is unique. And so you can do a very similar proof for infimum. So I'm going to say try proof for infimums. So try prove that infimums for sets are unique. So thus far we have seen examples of sets, and that when they exist, the least upper bound and the greatest lower bounds for B are in B, and some examples where they're not in B, right? Okay. So just another definition here. So let R be a partial ordering of a set A, right? And let B be a subset of A. If the, sorry, if the infimum of B is an element of B, it is called the smallest element. If the supremum of B is an element of B, it is called the largest element of B. And so remember, this definition is motivated by the fact that when we're considering a subset, and if it has a supremum or an infimum, sometimes the supremum and infimum are not elements of that set. So this definition pertains to the case where if the supremum and the infimum are elements of the set B. Okay. So now another definition. We've talked about we've talked about partial orderings for some time now, basically this whole lecture. And we can actually, we're sort of getting close to the end here, and we can actually get a little bit more structure here. And so remember when I started this lecture, I talked about the greater than or equal to relation, which had this comparability property to it, right? So a partial ordering R on A is called a linear order or total order. I don't know. I might say total order just because I think it sounds cooler, but I'll probably say linear order. I'll try to say total order. I don't know. On A, if for x, y in A, right, either x is related to y or y is related to x. So if you take two elements from a set with the partial ordering R, and it follows that one of these two statements is true for those two sets you've picked out, no matter what sets they are, then we call it a total order or a linear order. So again, it's a set that kind of has a little bit more structure to it. And finally, I'm not going to go too deep into these details here. Let L be a total ordering linear ordering, remember, on a set A. L is a well ordering on A if for all subsets B of A with B non-empty, B contains a smallest element. So this goes back to this idea. We talked about well ordering a little bit. So remember we talked about the natural numbers being well ordered. This is more of an abstract version of that. So if you have a linear ordering or a total ordering of a set, and then you can take that set, take any subset, and no matter what that subset is, it has a least element under that linear ordering, then you say it's a well ordering. And now we're going to finish this section with one of the probably one of the craziest theorems that exists in mathematics. This is called the well ordering theorem. Every set can be well ordered. I don't know why there's a hyphen there. Take it out. So just think about what this means. No matter what set you think of, I can come up with a partial ordering that would give that set, some sort of comparability, um, and no matter what subset you take of that set under my ordering, you would be able to find a a least element, which is a remarkable result. Think about, like, I mean, we're in a math class, so you might be thinking of sets of numbers and sort of things like that, but you can think of sets of people. You can think of sets of apples and oranges, right? You can think of sets of apples and people. No matter what set you give me, I can come up with a partial ordering of that set such that it's well ordered, which is a remarkable result. And okay, so that actually concludes section 3.4. I think this is quite a long video, and again, this is sort of a test run I'm doing to try to get this information out to you guys. And also, if you do it this way, I like doing it this way because then you have some notes that you can look at, and then if you need to review on something, you can always revisit some of these videos. So hopefully this becomes helpful. I know these aren't being done in sort of the most ideal situations with this whole COVID-19 going around, but I do think it's a good thing for me to do to get these notes out to you guys, um, to you people. So I hope this helps. I hope it understands. Please email me any questions. I'm available to help. Yeah, okay, cool. Thanks.